I want to continue on with our DMS notation where we left off in the last video. And I was getting ready to show you the calculator. We converted 20.14 degrees. We converted over to DMS notation. With that said, we were given 20.14 degrees. And with 20.14 degrees, we want to get rid of the decimal. So we want to break it down into minutes and seconds if needed. And if we need to round to the nearest second, we will. But with that said, the conversion factors is 60 minutes make a degree. All right? So 60 minutes is a degree, and 60 seconds is a minute. And you can see your notations. Single prime, or prime I should say, a single quote is our minutes notation. Double prime, or double quotes, is our second notation. So what we did is started converting. So we know if there's 60 minutes make a degree, and we've got 0.14 as our decimal, we want to get rid of that. So we'll go ahead and multiply by 60, and we did. And we got 8.4. And then we still had a decimal, so we're at 20 degrees, 8.4 minutes. And then we had to get rid of the 0.4, so we'll break it down into seconds. Since we know 60 seconds make a minute, if we have 0.4 times 60 is 24. And there's our conversion, 20 degrees, 8 minutes, 24 seconds. So, as we have that, let's take a look at the calculator real quick. On UTI, and I'll show you. Let's pull it up on the calculator. I'm going to circle the commands, and then I'm going to go to a different version so I can actually perform the command. But in order to access degrees, minutes, seconds, DMS conversions, you're going to hit your second key. So the second key and then apps. All right, so second and then apps in that order. All right, and that'll get you into what we call our angle menu. And within the angle menu, you will see the commands for degrees. You'll see the degree command, the symbol. You'll see your single quote, your prime command, which is your minutes notation. And you'll see a command that says DMS, which will convert a decimal to degrees, minutes, seconds. Now, in order to access seconds, you will not see the seconds command. The seconds command, and I'll look at it down here, is above the plus key right here. I'll circle here in red. And that's in the color of alpha. So in order to get seconds, you would hit alpha and then plus. So I just want to show that to you. So right now, let's pull up a calculator. I'm going to go ahead and look at our last problem. So I'll run through those commands with you. So here's a slightly different, maybe looking version than yours, but it's a TI application. And as I look at the command, let's take our last problem. We had 20.14 degrees. So I'm going to hit the second button and then the apps key, which is your angle menu. And here's where I'm talking about those commands. You see command 1 says degrees, command 2 is my single quote, which again is my prime or minute notation. And down at command 4 it says DMS, degrees, minutes, seconds. So I can take that decimal I just entered, hit command 4, and it'll ask me, do I want to convert 20.14 degrees over to minutes and seconds? And to answer that, we hit the enter button. And there it is, 20 degrees, 8 minutes, 24 seconds. All right, so again, that's converting, all right, over to DMS. Now I want to show you to go the other way. All right, say we were given degrees, minutes, and seconds. We want to get back to a decimal. So if you want to turn that around, let's type this in. So 20 degrees. Now to get 2 degrees, you hit your second button and angle, and that's command 1 here. And then 8 minutes, you hit your 8. You go back to the second button, back into angle. Command 2 is minutes. And then to get your seconds, which is 24 seconds, you're going to hit your alpha key. Hit the alpha key, and above the plus sign, you will see your double prime quote. And that'll give you seconds. All right, and there's 20.14, right? 7 divided by 50, all right, gives you 0.15. All right, so again, that'll allow you to convert it. Now mine writes everything as a fraction on this version, but again, that's going to be 20.14 if you've got your TI out. That should give you the decimal back on our TI-83 or 84. All right, so again, I just want to show you that DMS conversions, our calculator will handle that. So you don't need a calculator. We can do it by hand, knowing our conversion factors, knowing that 60 minutes makes a degree, knowing that 60 seconds make a minute. We can easily convert back and forth. All right, going back to our notes, maybe let's do the next one here together. Let's take example B. So let's convert 29.8 degrees. Let's convert it over to degrees, minutes, and seconds. Well, let's go ahead and get rid of the decimal. So we got 0.8. So as we convert, again, we know there's 60 minutes in a degree, so we'll multiply 0.8 times 60. And as we do that, we get what? 48.0. And that's, again, everything we need to convert with. So now I've got 29 degrees, 48 minutes. Now I don't have a decimal after the 48, so I don't have to convert any further. So I'm done. There's my conversion. 29 degrees, 48 minutes. And of course, you could check it on your calculator, right, if you wanted to. You pull up your TI. Let's go back to the calculator. So 29.8, go back to second, apps, command 4, hit the enter button, and there it is, 29 degrees, 48 minutes. All right. So again, I'm showing you conversions. Now I wanted to show you one where if we had to round, let's look at this last one. Let's convert it over to DMS. So let's put it in degrees, minutes, second notation. And let's let the calculator do that for us. So let's go back here to our calculator and let's type it in. So 30.2505 second angle, command 4, DMS. Got 30 degrees, 15 minutes, and 1.8 seconds. Now, we don't convert past seconds. We stop there with seconds. So there's no way to get rid of that decimal. So that's why they said round to the nearest second. So that's going to be 30 degrees, 15 minutes, and 2 seconds as we round 1.8 to the nearest second. So let's go ahead and write in our answer. So with our last example here in C, it's converted over to, again, 30 degrees, 15 minutes, and 2 seconds. All right. So again, that's conversions, DMS notation. So we'll see those kind of angle measurements. We're not always dealing with decimal degrees. Sometimes they'll get rid of that decimal. We'll convert it over into minutes and seconds. Speaking of more calculator type problems, I want to look at some different trig function values with some different acute angles. These are not any of our special angles. These are not 30, 45, and 60, which we already know the function values for. We've proven earlier. But it says find the trig function value rounded. So I want to get an approximation to the nearest 10,000. It says round to 4 decimal places. So we've got a few different examples. We got one with tangent. Let's go ahead and do example A. So I have tangent of 29.7 degrees. What does it equal? So let's go back to, pull up our TI. All right. Now, one thing I want to make sure now in my TI calculator, hit the mode button. And before you begin, notice my mode. This is the default mode on your TI-8384. It's radian. See how radian is highlighted? So use your arrow keys on the right-hand side and go down here and convert over to degrees by hitting enter. Because remember, we're given a degree measurement. We're not given a radian measure. So now that we're in degree mode, right, we can easily type that in. So again, what are we looking for? In this example, we want tangent of 29.7. All right, so let's go ahead and type that in. So the tangent of 29.7 degrees. Again, notice that's degrees. I'll hit the enter button. I get 0.50 or 5703899. Again, irrational number. Not any decimal, my calculator rounds it. So we want to go to 4 decimal places. So that means we're going to go to that 3 and round it up because we got an 8 next to it. So 0.5704. 0.5704 rounded. All right, so again, that's using just the calculator to get a function value. Now, not a whole lot going on with that, but I just want you to be familiar with your calculator, which we've looked at before. But I do like, if we had to use a problem like this as a test question, you would probably expect to see something like example B if I wanted you to use your calculator, just because you got to do a little bit of work on your calculator to find the value, to just type it in as given. For example B, it says secant of 48 degrees. Find its function value. What does it equal? Well, if you remember, we don't have a secant function shortcut key. We have sine, cosine, and tangent. So as I mentioned earlier in our lecture, when we're dealing with our reciprocal functions, secant, cosecant, cotangent, let's rewrite them using our reciprocal properties. So secant of 48 degrees is the same exact thing as saying 1 over cosine of 48 degrees, right? Because they're reciprocals. So again, using reciprocal properties, right? These are reciprocal functions. So let's reciprocate. And now we can type it in easily. So 1 over the cosine of 48 degrees. Now we go back to our calculator. So let's pull up our TI-84. And again, we have our sine, cosine, tangent keys. So if we want secant of 48, that's 1 divided by the cosine of 48 degrees. We're already in degree mode. And we get 1.49447. So round into 4 decimal places. That'll be 1.4945. So let's go ahead and put in that function value. So 1.4945. All right, now let's do the last one. Go ahead and do example C. In this one, they're giving us angle measurement with DMS notation. We've got 84 degrees, 10 minutes, 39 seconds. So instead of decimal 84 point something degrees, they're getting rid of that decimal by writing in terms of minutes and seconds. Now, we don't need to do any conversions. Remember, our calculator does handle this notation. So let's go ahead and look at that one on our TI. So let's go ahead and pull up the calculator. Now I'm going to go to my different version because my other calculator doesn't allow me to type in those on my application. So let's go pull this one back up. So in here, now I got to make sure my mode on this one's in degrees. And it is. So I'm okay with this one. But let's type it in. So we got the sine. So hit your sine key. And then we have 84 degrees, 84. Now remember, degrees is in the angle menu, command 1. And I've got 10 minutes. So remember, second, apps key is angle, command 2. There's my prime or minute notation. And then 39 seconds, I hit the alpha key and then the plus sign on your TI-84. And you hit your enter button, and you'll get your output. And you should get, all right, until you enter, you should get 0.9948 rounded. All right, and I'm getting a error message on mine. All right, but again, that's your output. Let's go ahead and put that in. So 0.9948. So hitting the enter button will allow you to get that. So again, my TI app is not going to allow me to show you that on there, but you see how to enter it. So again, remember, go in that angle menu, right, and you type it in, hit the enter button, you're going to get this answer. But there it is, 0.9948. All right, so again, that's angle measures, different acute angles, angles measuring between 0 and 90 degrees. And the reason we're dealing with these type of angle measurements right now is because we're looking at different right triangles, right? In our different problems, we've been using right triangles to apply applications. All right, let's move on. So moving on here to our next page. All right, looking at our inverse property. I want to show you the application of inverses. It says finding the acute angle measurement, say theta, for the given function value y. If y is equal to the sine of angle theta, then theta is equal to sine inverse of y. So using the inverse property, we know with inverses we interchange our relating variables. So our relationship is the relationship between theta and y, the angle and the value. So as we swap those out, we get into inverse. So theta and y have been swapped out, so that gives us sine inverse, right? You see your superscript -1, our inverse notation. So using inverses will allow me to find the angle measure. All right, so let's show that in some examples. So for example, in 72, it says the tangent of theta is equal to 2.032. All right, well, if we want to find theta, so that implies theta is equal to tan inverse of 2.032. So again, use your inverse characteristic. So second tan, right? If you go to our calculator. So let's go ahead and look at that. Pull your calculator up, and let's see if we can type that in together. I'll get my TI-84 back out. So second button and tan, that's your tan inverse. So both sine, cosine, and tangent, you'll see sine inverse, cosine inverse, and tan inverse. So again, second tan is tan inverse, 2.032. I get 63.79, so let's round it to the nearest tenth. So that would be 63.8. So 63.8 degrees, right, would be the angle measurement. So theta, approximately 63.8 degrees. So there's our angle measurement. Again, acute angle, an angle between 0 and 90. But again, finding that using the inverse, right, operation. All right, let's do another one. Let's take another example. All right, tell you look at, for example, go down here. I like example 80. Let's do 80 together. In 80, I've got cosecant theta equal to 1.147. Now, I like this one. This would be a good test question. And the reason I say that is, remember, we don't have a cosecant shortcut key. So let's first rewrite it. All right, rewrite with sine. So that implies sine theta is equal to what? 1 over 1.147. So remember, these are reciprocal functions. So we'll make that note. We're using our reciprocal definition. So sine theta, so the reciprocal of 1.147 is 1 over 1.147. And now we can use inverses. So to find theta, theta is equal to sine inverse of 1 over 1.147. So let's go ahead and type that in. Let's see what we get for our angle measurement. So again, we didn't have that cosecant key, but we have sine inverse. So second sine is sine inverse, and then 1 divided by 1.147. And out comes our angle measurement, 60.7 degrees, round to the nearest tenth of a degree. So 60.7 degrees would be the angle theta. All right, so again, that's using a calculator, right, to find the angle measurement. Now, these were angle measurements, right, that I don't expect you to know. They're not our special angles, right? We shouldn't recognize off the bat what those values represent angle-wise. Whereas we go to our next slide, you shouldn't even need a calculator. So I want you to take a look at this next page here. Now, this is going back to our special angles. Let's find the acute angle theta, same direction as our last set of problems. Find theta for the given function value y. And again, remember, just for example, inverse properties. If y equals sine theta, theta equals sine inverse of y. Y equals cosine theta, theta equals cosine inverse of y. Right, y equal tan theta, theta equal tan inverse of y. So inverses, swap it out, allow us to solve for it. Now, when I look at problem 84, for example, in 84, cotan of theta equals square root of 3 over 3. Well, I recognize that as a special angle measure from one of our acute angles we talked about earlier. If you remember, cotangent of theta, square root of 3 over 3, all right, go back to your shortcut. Let's look back at that review. All right, we know cotan of theta holds the value of square root of 3 over 3 at 60 degrees. Right, tan of 30 is square root of 3 over 3. Cotan of 60 is square root of 3 over 3. Remember in the complementary angle theorem. So using cofunction properties. But yeah, I already know that's cotangent of 60 degrees. So yeah, in 84, we already know. I don't need a calculator on that one. That's one of my special angles. So yeah, if cotan theta equals square root of 3 over 3, that implies theta is equal to 60 degrees. Now, if you wanted to check that on your calculator, you would need to rewrite it, right? So you could, or we could say tan theta is equal to 3 over the square root of 3. We could reciprocate, right? Reciprocal functions. And then you could use tan inverse, right, of 3 over square root of 3. So go to your calculator just to check it. We'll put that in our calculator. So second tan of 3 over square root of 3. So second tan 3 divided by the square root of 3. And as we do that, right, what do we get? 60. Here's our 6-degree angle. But we didn't need a calculator. I could recognize based off that function value, right? That's one of my special angles. So remember, I told you want to have these memorized. You want to know the sine of 30 is 1/2. You want to know the cosine of 30 is square root of 3 over 2. You want to know the cosine of 60 is square root of 3 over 2. Right, or 1/2, I should say. You want to know sine of 60 is square root of 3 over 2. Tan theta, again, you see your table here. These are values we're going to keep seeing come up, which we proved in this section using a little bit of geometry, using some right triangle trig from our isosceles right triangle and from our equilateral triangle as we drop the perpendicular to form a couple of different right triangles to use and prove 30 and 60s. But going back to these, so when I go to problem number, for example, 86, right? We know that 86 sine of theta is 1/2. I know that's the 30-degree angle. So I know in 86, sine of theta is equal to 1/2. That implies theta is 30 degrees. I don't need a calculator for that. But you can put it in your TI if you want, right? Go in the calculator to do it, right? You can hit second sine. We can go to our calculator, right? What's second sine of 1/2? 30 degrees. So again, these are special angle measurements. You look at, for example, I already know 92. Secant theta, square root of 2. Remember, square root of 2 is our hypotenuse on our isosceles right triangle using those 45-degree angles. I know a 92, theta is 45 degrees, right? Now, I could go to my calculator. I could write that as cosine. Cosine of theta is 1 over square root of 2, right? And do the inverse characteristic, right, to find that. But again, this is a special angle. All right, when does tan of theta equal square root of 3? Well, that's 6 degrees, right? I know in 90, theta is equal to 60, right? You can go back to your measurements, right? Tangent of 60, again, one you should know is square root of 3. So here's theta equal to 6 degrees. Cosine of what is 1/2? Cosine of 60 degrees. I know here in example 85, theta is 60. All right. So again, these are special angles. We don't need a calculator to do the work. We know in 88, for example, when does cosine hold a value square root of 3 over 2? That's at 30 degrees. Theta is 30 on number 88. So those should be quick and easy because these are dealing with our special angles. So these are our special acute angles. Anytime you see the word exact, you know a calculator is not needed in order to find it. So these are our special angles, 30, 45, and 60. All right? Moving on, let's take a look at problem number here at the last page, slide 16. This is application. And sort of summarize right triangle trig. Let's see an application of right triangle trigonometry. Let's read through this and see if we can get a picture of what they give us and see if we can figure out how to find the unknown using what we learned in this section. It says, as a hot air balloon began to rise, the ground crew drove out 1.2 miles to an observation station. It says the initial observation from that station estimated the angle between the ground and the line of sight to the balloon is a 30-degree angle. Right? Approximately, how high was the balloon at that point? So there's our question. So how high is the balloon after driving out a distance 1.2 miles to an observation station and looking up to it? All right, we're assuming that wind velocity was low and that the balloon rose vertically for the first few minutes. It says round your answer to the nearest tenth. All right, so let's construct a pit. Let's get a visual. We got a word problem. We want to take this given information and get a visual of that. So we're dealing with a hot air balloon rising here in the sky. All right, so let's go ahead and look at that picture. So I'm going to draw in the ground here. And I'm going to go ahead and draw this hot air balloon that's rising up in the sky. All right, and let's go ahead and get a picture. I'll draw my balloon here. So here's my hot air balloon. All right, and then again, I'm looking at the distance right here that's traveling. If you want, let's put it in a different color. I'm going to put it in blue because this is the unknown in this problem. How high is this balloon in the air? So this is our unknown here, x, the height. All right, there's the height of balloon. So remember, it rose vertically. Very low, it says wind velocity, so it wasn't moving east to west. It was going straight up. With that said, what else did they give us? They said we were going to drive out 1.2 miles to an observation station. And it says the angle between the ground line of sight balloon would be 30 degrees. So let's show that in our visual. So as we go back to our drawing here, right, we drive out a distance of 1.2 miles, and we'll say our observation station is right here. So here's the station. So we drove out here to this distance. This is 1.2 miles. All right, and it says the angle between the ground and the line of sight to the, again, line of sight is looking up the balloon, see how high it is. All right, it tells us that. So let's go ahead and draw in that line of sight. There's the line of sight from the observation station. And we know its angle between the ground and the line of sight was 30 degrees. That's what we call our angle of elevation, something we'll talk about in our next section. We get into solving right triangles. But what we've done, you can see in our picture, we've constructed a triangle. And we've constructed a right triangle. Right? Because we've got a hot air balloon that rose vertically with respect to the ground that's sitting here horizontally. So that makes a 90-degree angle, right? They're perpendicular. So we've got a right triangle. And in this right triangle, right, what are we looking for? We are looking for the height, which I've written here in blue. Let's find the height of the balloon. What can I use to help me find x? What trig function would use the two legs of the right triangle? What trig function would use the opposite and adjacent side to this angle theta? And we all know that's tangent. So let's use a tangent function. So again, what does this imply? This implies the tangent of 30 degrees is equal to opposite, which is x, over adjacent. Opposite over adjacent. That's our definition. So what have we done? We've set up a equation to go solve. So to find x, let's solve x. So our next step, right, is we solve x. Right, we need to clear out the fraction. So we would multiply both sides by 1.2, right? We got to get rid of its coefficient. So using multiplication property equality, we multiply both sides by 1.2. So as we do that, we have what? 1.2 times the tangent of 30 degrees equal to x, right? So again, we got rid of the coefficient, and we can divide out the 1.2s, and there's our solution. So what does x equal? 1.2 times the tangent of 30. So let's go put that in our calculator, right? And let's go get our value. Now, tan of 30 is square root of 3. If you wanted to, you could simplify, but I'm still going to put it in the calculator, so I'll let it do the work. So 1.2 times the tangent of 30 degrees, or again, square root of 3, gives us a decimal value. Now, we want to round it to the nearest tenth, I think it said. So it says 0.7. Now, this is in miles. All right, now, so go back to that. Let's go back. It said round ants to the nearest tenth. So that implies x is equal to 0.7 miles. So with that, now if you wanted to, what is 0.7 miles? You could break that down in terms of feet. Right? We do know that 5,280 feet equal 1 mile. So we could take that and convert it. So let's go ahead and write what that would be in feet. Let's multiply by the conversion factor just to break it down a little bit further. And what's 0.7 times 5,280? 3,696 feet. So 3,696 feet. Right? But again, using right triangle trig to solve for my unknown. So again, that summarizes 6.1. We've gone through our definitions of our 6 trig functions using right triangles, right? The ratio of the lengths of the different sides. Sine opposite over hypotenuse, cosine adjacent over hypotenuse, tangent is opposite over adjacent. And of course, they're reciprocals. Cosecant, which is reciprocal of sine, so it's hypotenuse over opposite. Secant, which is reciprocal of cosine. Remember, cosine is adjacent over hypotenuse, so secant would be hypotenuse over adjacent. And of course, cotangent, reciprocal of tangent. If tangent is opposite over adjacent, cotangent is adjacent over opposite. So inverses, another highlight of this section. We look back at inverses. They allow us to find our angle measures. Remember, again, we can swap out using the inverse characteristic to allow us to take a function value, right, to get to the angle. So that instead of finding the function value, maybe we got to find the angle. If that's the case, inverses will do that. And of course, remember our special angles. We will see those throughout the semester. We're going to keep referring to these. So eventually, if you don't have them memorized yet, you will. All right, we'll keep working with them. So you'll see those throughout this chapter and as we move through this semester. So I hope that helps you with section 6.1.